Alright, so here's the next in our series of videos on systems of equations. There's a couple more to follow this with a little bit of theory in them, I suppose. But this is an example of some of the applications, things that we've mentioned in the past that lead to systems of equations. We mentioned that questions about span, questions about column space, that these are really problems that need to be solved by solving systems of equations. And at the time we didn't have methods for solving, so we left this alone, right? Now, remember the definition of span. So the span of a set of vectors is all of the linear combinations that you can form with those vectors. So if I tell you that a vector w belongs to the span of these vectors v1 up to vk, what I'm telling you is that I can write w as a linear combination, right? So w is a linear combination of those vectors. What I don't know is what values x1, x2, I don't know what these values are, right? So my job, if I want to know, well, one, whether or not w does belong to the span, and if it does, what are the coefficients? Well, this amounts to solving a system, right? Because if v1, again, if v1 looks like a11 down to maybe an1, right? x2 times, so v2 looks like a12 down to an2, right, and so on up to xk, and vk looks like a1k down to ank, and if w looks like, let's say, b1 down to bn, right, well, we can see what our system is going to be. a11 times x1, a12 times x2, up to a1k times xk, right? And so we could also write this, right? We could write this as a times x is equal to b. Well, not b, it's w, so let's leave it as w, right? W, right? Where x is this guy, x1 to xk, and A is the matrix formed by putting in these vectors. Okay, so you can guess what you do. We got to solve our system, so how do we solve? Well, we're going to reduce the augmented matrix A W to, well, row echelon form at the very least, possibly reduce row echelon form, depending on how we want to go. Okay, so let's try this out. Here's a vector w, here are some vectors, v1, v2, v3. We want to figure out if w belongs to the span of these vectors, so we set up our augmented matrix. -1, 2, 0, 0, 2, -3, 1, 0, 4, okay, and then 2, -4, 3, right? So here's your v1, here's your v2, here's your v3, here's your w. And we proceed. So, alright, we've got a, well, it's a leading -1. Let's do this first. I'm going to do row 2 plus 2 row 1 and make that my new row 2. So what happens when I do that? 2 minus 2 gives me a 0. 2 plus 0 is 2. 0 plus 2 is 2. And -4 plus 2 gives me a -2. While I'm at it, let's switch the signs on row 1, because I do want a leading 1 there. 1, 0, -1, -2. I just want to be careful if you try to do these two steps at once. It's very easy to get a sign error, right? So let's be careful on that. 0. Didn't do anything down here, so let's just recopy that. 0, 3, 4, 3. Okay. Easiest way to get my next leading 1 is to divide that second row by 2. So 1/2 row 2 becomes my new row 2. 1, 0, -1, -2, 0, 1, 1, -1, 0, -3, 4, 3. Okay. So next up, what do I got to do? I got to add I got to use my second leading 1. I got to use this leading 1 here to get rid of that minus 3. So we got to do row 3 plus 3 row 2. Make that my new row 3. 1, 0, minus 1, minus 2, 0, 1, 1, minus 1, 0, 0, 7, 3, minus 3, 0. Okay. Gets me down to there. Excellent. And notice that we can answer yes. We can already answer yes, right? Because I got a leading 1 in every column. You might say, wait, there's no leading 1 in that last column. Well, that's true, but I can, let's just squeeze in one more step, and I won't bother to write it down. 1 over 7 row 3 becomes my new row 3, and then this 7 becomes a 1. There's my leading 1. Okay, maybe I want to figure out from here what values of x1, x2, x3 are going to do the job. But I can already see that this one here tells me that that x3 should be 0. 1 times x3 should be 0. And if I were to back substitute, well, then I'm going to get, I'm going to get zeros in here and in here. And so this says, if this is going to work, this says that x1 should be minus 2, x2 should be minus 1, x3 should be 0. Alright, why don't we make sure that we didn't mess that up? If I do minus 2 times v1, minus 1, 2, 0, okay, there's my x1 v1, minus 1 times 0, 2, minus 3, there's my x2 v2. And, well, 0, I'm not going to write the other one, it's 0, right? So what do we get? 2 times 1 is, minus 2 times minus 1 is plus 2, subtract 0 gives me a 2. Minus 2 times 2 is minus 4, subtract 2 more, gives me a, oh, I've messed something up, haven't I? Minus 6. 0 minus minus 3, 3. Something has gone wrong in the middle. Alright. Can you guys find my mistake? Should we go back and look, or should we brush this off and move on? I think we should check to, why don't we find our mistake? This is the nice thing about most of these problems in linear algebra. If we make a mistake, we can go and find it. So let's look for our mistake. Did I copy everything down correctly? I did. Alright. Did I do my first row operation correctly? Minus 2 gives me a 0. 2 plus 0 gives me a 2. 0 plus 2 gives me 2. Minus 4 plus 2 gives me minus 2. And I changed my signs. That last row is still fine. Okay. Divide through. So far so good. So then I'm multiplying through by 3. 3 minus 3. 0, 7, 0. Okay. Seems alright. X1 is minus 2. X2 is minus 1. Alright. Where is my mistake? Can't find it. Can you guys find it? Alright. We'll have to come back to this one later because I don't see my mistake. Okay. Alright. Let's move on. Here's another example. Okay, I want to figure out for what values of A, B, and C this vector W, ABC, belongs to the span of these vectors. So we set this one up the same kind of way as before. We set up our augmented matrix. Minus 3, 1, 0, 0, 1, 6. Well, this time we don't know what A, B, and C are. We just leave them hanging out there on the other side. But we can still reduce. So how do we reduce? We've got our first leading 1. we got to use it to create zeros. So row 3 plus 2 row 1. That's going to be my new row 3. 1 minus 3, 0 A, 0 1 1 B, 0 minus 6, and then 6, and oh, sorry, I'm missing a minus sign. That might cause me some trouble later on, wouldn't it? And then C plus 2A, right? I'm adding 2 times row 1 to row 3, so 2 times A gets added to C. All right. Well, now I've got leading 1, leading 1. I might as well get rid of that minus 6. So next up, I'm going to do row 3 plus 6 row 2. That's going to be my new row 3. 1 minus 3, 0. A, 0, 1, 1. B, 0, 0, 0. And then C plus 2A plus 6B. All right. So now we can answer the question, right? Because we got zeros on the left, if this system is going to be consistent, right? So a consistent system corresponds to answering yes to the question of whether or not W belongs to the span. So what do we get in this case? Well, it's going to be all values of A, B, and C, such that 2A plus 6B plus C equals 0. Right? So that lets us describe the span. In fact, we could say the following. We could say that the span, if I write C equals minus 2A plus 6B, right? We could use that to describe the span. We could say, well, you know, in fact, A, B, C looks like A, B, and then minus 2A minus 6B minus there, right? And you could plug that in, and you could say, well, you know what this is then? This is A times 1, 0, minus 2 plus B times 0, 1, and minus 6. And what's interesting is that that tells you that, you know, really the span of V1, V2, V3, you know, it's just the span of V1 and V3. V2, unnecessary. I can throw it away. I can get rid of it. By the way, that's really because I solved for C here in terms of A and B. If I had solved for A in terms of B and C, you know, or B in terms of A and C, you know, I would see different vectors showing up. Okay. So far, so good. Another reminder from class. If we have a matrix, right, we can look at the columns of that matrix as vectors, and we mentioned in class that we can define the span of those columns to be the column space of our matrix A. And we mentioned, right, we connected this back, you know, if we think in terms of the previous example with span, right, the span of these columns, we said, well, this is, you know, this is equal to the set of all you know, y such that A times x equals y for some x, right? So it's the another way to say it is it's the range of the function, this matrix transformation t of x equals A times x. Okay, so range is something we might want to compute for a function. How do we compute the range of this particular function? Well, using Gaussian elimination. So what we do is we take our matrix, we reduce it down to reducer echelon form. In fact, it's enough to really, you know, by the time you get to row echelon form, you know where the leading ones are. So what you do is you find the columns where the leading ones happen. Okay, you figure out which columns get leading ones. Then you go back to the original matrix. So these are the original columns. And the corresponding columns in the original matrix, those are the ones that generate your column space. So basically, this gives you an algorithm, so we know that the problem here is that, well, we write the column space as the span of these vectors, but some of those vectors might be redundant. Like in the previous example, right, it was enough to just have v1 and v3. v2 was redundant. We didn't need to keep v2. So Gaussian elimination essentially gives us a means of determining which vectors are redundant. So we figure out which vectors end up with leading ones. We keep those ones. We throw away all the rest. So here's an example. How are we going to solve this? So the way we solve this is we reduce. So first thing I'm going to do here is I'm going to swap row 1 and row 2 because I want to get my leading 1 up top. 1, 1, 2, 0, 2, minus 1, 4, minus 3, 3, 1, 2. Okay. You know what, actually let me make this a little more interesting. Let's make that a minus 3. Okay. Alright, so now I'm gonna do row 2 minus minus 2 row 1. I'm gonna do row 3 plus 3 row 1. 1, 1, 2, 0, 0, 0, minus 5, 4. 0, 0, 5, sorry, not 5. 3 times 2 is 6, plus 1 gives me 7, and then 2. Okay, and then I can do, what can I do from here? From here I guess I'm going to do minus 1 over 5 row 2 becomes my new row 2. So 1, 0, 0, 1, 0, 0, 2, 0, I'm going to go 1, minus 4 over 5, and then 7, and then a 2. And so then I can do row 3 minus 7 row 2 and make that my new row 3. 1, 2, 0, 0, 0, 1, minus 4 over 5, 0, 0, 0, 2 minus 7 times minus 4 over 5 is 10 over 5 plus 28 over 5, 38 over 5, right? Well, the last thing I would do is I would do 5 over 38 row 3, make that my new row 3, and then this becomes a 1. Okay, so where are my leading ones? They're here, and they're here. Okay, this one is not a leading 1 because it's not the first non-zero entry in its row. There's a 1 in front of it. Okay, so there are leading ones in columns 1, 3, and 4, and that means that the column space of A is the span of 2, 1, minus 3, row 1. I skip row 2, I go straight to row 3, and then 4, 0, 2. And actually, one of the things you could do here is one of the things that this theorem tells you. I mean, it tells you it's a basis, right? And we didn't really talk a lot about this idea of a basis, but a basis is a set of vectors that not only spans, it's also independent, right? So what we've done is we've thrown out the dependent vectors. We've kept the essential ones. And so you've actually got 3 independent vectors in R3, and with a little bit more theory, more than we cover, we could argue that in fact those 3 vectors are guaranteed to span all of R3. Any 3 independent vectors in R3, it turns out they form a basis, right? They don't all lie in the same plane, so they actually generate the whole space. Okay, So that is it for now.